We're going to go through a full breakdown of both the kinetic and kinematic analysis of my first counter-movement jump since my Achilles tendon rupture surgery that happened approximately 124 days ago. I'm super excited to showcase this with you, to kind of show the phasic elements, and then how I go about my testing as a sports scientist, and how I can compare this data with the prior data I had, as I was lucky enough to accumulate over 200 tests. So let's get right into it. So first thing that we're seeing here is myself in a standing position, my hands on the hips to delay from any arm swing. We just do this just to control for the environment as much as possible. The arm swing can account for quite a bit the output metrics that we see, and also the force time metrics that we see are going to be a bit smoother. And we just want to control just for lower limb power and get the legs. So as we start this video, staying still, we see the flash on the screen, we go into this unweighting phase. Notice that we have this deviation going down because we're sinking our center of mass down, unweighting of the plates, going right into the braking phase, and into the propulsive. Now notice here, we've got some arrows, circles here. We're gonna go back through this, talk about the numbers and also what we're seeing. Perfect, we have the landing phase, the initial spike, the peak landing forces, perfect. And notice I have quite a bit of trunk flexion going down to absorb a lot of that force because I don't want to put it onto the leg, and that's just a natural compensation. So going back to the beginning of the video, going into the unweighting phase. Now just to give a few numbers in terms of context, notice going into that dorsal flex position, loading, really looking at to see if there's any repercussion or vertebrations that are occurring at that right side in terms of whether it's able to withstand the amount of force I'm putting down into the plate itself. Now, in terms of our left or right braking forces, the peak force was only a 3.07 difference. On average, about 1.29% difference. It's not significant at all, so there was no significant change from the 204 prior test I had. Now, if we look at the average forces of the left and right in terms of deviation, there's only a 2.36% deviation. Granted, my average jump height is about 24.31 over 204 total tests. This jump was only 9.5 inches, not the highest in terms of what my average are. My healthy side, 872 newtons of force. My Achilles side was 817. From the outside looking in, you're like, okay, that's not that big of a change. But in terms of the overall, in comparison to prior, yes, we're going to have a significant difference no matter what, due to the fact that the jump height, the overall output is a lot smaller, being at 9.5 inches compared to that 24. There was a 12.5% decrease in the healthy side, but overall there was a 23% change in my right side, fairly significant. So we have that macro. It's not enough just to look at the left or right differences from a standstill, but knowing that I have prior data, this is why it's so important to have athletes testing as soon as possible, just to have comparative analysis with current, past, and future. Next up, the braking rate of force element. So rate of force element, how much am I willing to put force into the ground, and you're producing yourself, so you're not absorbing force per se, as we commonly put out there. There was a 13% reduction on average. I've got a little less than 5% on average in the prior test when I was healthy, and there was only an 8% change, which is not significant by a large status. Now both the left and the right side both had a deviation of about 70%, to take that with a grain of salt. Now, although there was a comparative difference with all the percent changes with both left and right, when we're looking at the braking phase time, I'm using compensatory patterns to compensate for what I'm trying to put my body through and the outputs I'm trying to gain. And athletes are naturally going to want to do this anyway. So it's something to keep a lookout for. The braking phase time increased by 51%. And as we know with any sporting outcomes that need to occur right now, usually within 250, 200 milliseconds to achieve a successful sporting outcome. This is super important. Usually about 0.15 seconds, and increase this to 0.23 seconds. The relative force at minimum displacement. So in comparison to my own body weight, what is the amount of force at the very, very bottom at the amortization phase, in this case, willing to undergo or put myself through? And this is a great metric to look at in terms of neuromuscular fatigue as well, just because it's very, very hard to self-regulate right at the bottom when you're doing a very explosive, ballistic, plyometric movement. In this case, I was 192%, but my average is about 312% of my body weight. Fairly significant. It's about 120% change. And then moving into the propulsive phase, I zoomed in here just to showcase what amount of dorsiflexion and plantar flexion and toe off was occurring. But notice that they seemingly look like they are providing the same amount of force. Now, the timing in which the force is induced into the ground reaction forces, and what's actually being uncovered is very, very different. And if we look at just the absolute metrics of what the left had, what the right had, it can paint a messy picture. Going to that toe off position, we have these arrows on both the left and the right. Notice that the toe off is much, much higher in the left healthy leg, and it occurs a little later. A lot of times when people have these asymmetrical imbalances due to injury, the forces might be the same, but the timing in which the forces occur are going to be slightly delayed and a little higher on the uninjured leg to kind of compensate. And from the naked eye, it can look totally fine. And if you're just looking at the absolute metrics, that can be a problem too. For instance, if we look at propulsive phase, the peak forces, the healthy side had 1,264 newtons, Achilles side had 1,039 newtons, which is not a huge difference between the two. It's actually only 9.77% differences, which is significant, but it's in the grand scheme of things, it's not that significant. But when we look at the percent change from the prior test, yes, we had a decrease because the overall output of this jump was only 9.5 inches instead of the average of 24, 8% change on the healthy side. But on the Achilles side, there was a 26.5% change, which is very, very large. So in the grand scheme of things, if we just look at the left to right differences and deviations, that is not enough. We got to look at how those compare in those deviations compared to past tests on an individual basis, not just the comparative. When we look at the average forces, the healthy side had 872 average force generation over the propulsive phase, and the Achilles side had 817 newtons, which is not a huge difference in terms of just 1-to-1. But then you have to look at the prior past data, and those comparative analysis, there was a 12% change on the healthy side, and there was a 23% change on the unhealthy side. Now let's move on into the landing phase, touching down here. And then notice on that right side, we have reverberations or the repercussion lower leg. This could be a number of things: generalized strength, capacity of the tissue to handle that amount of stress, or it could be a combination of things of that with neuromuscular ability or willingness to undergo that load. The landing stiffness did go up quite a bit though. It had a 35% increase. This cannot be taken with a 1-to-1 from a 24-inch height compared to a 9.5-inch height. That's why those depth drops or depth jumps are so important. Worlds of difference. Although we did have this increase in landing stiffness, which is generally seen as good if that's what you're going for in terms of stiffness qualities, which is usually not assessed until or unless it is a drop jump or a depth jump. Although I've taken a lot of those jumps before, those motor patterns probably haven't caught up to me as much as I'd like. Those are the highest forces that were incurred over the course of the jump, where the landing itself. But that's just an increase. I want to put that out there as well. The left and right peak force in terms of the landing was only a 5.8% difference, and the left-right average force was a 7.91% difference. One thing we do want to look at is that reverberation, the repercussion of the lower leg. Track these changes in terms of asymmetries, and those asymmetries in comparison to past asymmetries. Notice the overall theme is the past outputs that really drive the difference home in terms of what needs to be worked on, what capacities need to be worked on from a motor development, physiological tissue development stage, basing that information so that I can progress forward with different activities, whether that's running, jogging, time duration, the amount of load, the overall volume of stimuli I want to induce on myself. These could all be pulled some way, shape, or form from the data that we see just on a simple counter jump. I hope you did like this video. I know it was very lengthy. Talked about a lot of numbers. If you happen to like it, please let me know.